Thank you. Hi again. I'd like to, one more time, invite you to the Pan American Conference that is going to be held in Chile in November 2024. A few key dates. The conference itself is from the 12th to the 16th of November. The submission of abstracts is until July 31st, the first call, and then the second and last call till August 31st, so you still have time to write and submit your abstracts. We have these themes that should encompass everything that we all do. Chile is a geotechnical country. We have earthquakes as big as they get. We have mining, which has several challenges in every aspect that you can think of geotechnical engineering. Geothermal, a lot of renewable energy, in new installation, infrastructures. The venue is going to be La Serena, which is a city that has an airport right there. It's like an hour from Santiago, which has very nice scenery and tourism that you can do nearby. Very interesting things, both on the mountains and on the valley and the ocean, of course. There's a short video inviting you. Many large observatories are there because of the clear skies. Should have a music. That sounds better there. Through networking. Vineyards are right there in La Serena, very close to where we'll be. Yeah, I think we're streaming in about a minute, so I'll cut it there. And I'll again invite you, save the date, submit your abstract by August 31st, hopefully before that, and you'll be welcome. Bye.
Thank you, Gonzalo. All right, so welcome to the closing session of Geo-Risk 2023. So this session is kind of special as it is dedicated to papers and authors that have won ASCE awards in the last 3 years and which have Geo-Risk as a theme. These award-winning authors and papers were nominated by the Risk Assessment and Management Committee of the Geo-Institute of ASCE, which is also the committee that is organizing this specialty conference. This has not been done before in previous specialty conferences, so we hope that the session will be interesting to all authors and to all attendees. So I will start with the first paper that won the 2021 ASCE James R. Croes Medal. Professor Bob Gilbert will be presenting this paper. Bob is the chair of the Department of Civil, Architectural, and Environmental Engineering at University of Texas at Austin. Prior to joining UT, he practiced as a geotechnical engineer for 5 years at Golden Associates. His technical focus is the assessment, evaluation, and management of risk for civil engineering systems. Dr. Gilbert was awarded the Norman and Croes medals from ASCE and an Outstanding Civil Service Medal from the United States Corps of Engineers. In 2020, he was elected to the National Academy of Engineering. Throughout the years, Bob has been a mentor, a role model, and a source of inspiration to a large number of students and colleagues in the geotechnical engineering profession. I am lucky to be one of them. Please join me in welcoming Bob to the stage.
Thank you, Shadi. That was more than 2 sentences. I'm going to talk about a paper that I'm not the first author on. Jimbo Chen was the first author. He's out in the Gulf of Mexico drilling right now. I want to acknowledge all the other co-authors. Their affiliations are given here at the time the paper was published. Many of them have gone to different roles. And I want to acknowledge there's all sorts of other people that have been involved in this over the last 30 years since Hurricane Andrew and even before that. Alan Cornell, Fred Moses, Bob B., Frank Puskar, people that have been working in this industry for a long time and doing everything we can to learn from how systems actually behave under real loading conditions. And none of this work would have been possible without a whole village of people looking at it. The offshore oil and gas industry is a big part of oil production and gas production in the United States. It's about a fifth right now of all of the production for the United States. At one time, about 10 years ago, it was up to 35%. And the only difference is all of the fracking that has created in the last 10 years more production onshore. The production is primarily from these fixed jacket structures. There's about 4,000 of them in the Gulf of Mexico. They're very tall buildings. They're in anywhere from 300 to 500 feet of water, and they stick up above the water line another 100 feet or so. They're subjected to significant waves plus winds and currents due to hurricanes, and the structures themselves are designed to withstand those forces using a structural jacket above the mudline and a pile foundation system below the mudline, which is made up of steel pipe piles that are driven on the order of 300 feet below the mudline. And since 1992, we've had a number, 6 actually, hurricanes come through the Gulf of Mexico, pass through one part of the Gulf that had offshore oil and gas platforms located in it, and every one of those hurricanes had loads that were beyond the design load for these structures, so they're a great opportunity for us to learn how well do these platforms perform. Here are the paths of those 6 hurricanes. The yellow dots are those 4,000 platforms, and the red dots are the hundreds of platforms that were destroyed in those 6 hurricanes. Here's an example of what a destroyed platform looks like when you go out in a helicopter after the hurricane. So these are real failures. These are not notional failures. These are real failures. As many platforms as were destroyed, there are many more platforms that survived, platforms that survived even though they were loaded beyond what they were intended to be able to withstand. Here's an example of a survived platform. You can see that the girders in the cellar deck have been bent and the railing has been bent, so the waves got up to the deck of that structure, put loads on it beyond what it was designed for, but that platform was able to withstand those forces. So the whole goal of this is to learn everything we can from how these systems are performing compared to how we think they would perform based on design. These structures are designed using 3-dimensional nonlinear finite element methods. We try to do the best we can in modeling the structure, modeling the foundation system, modeling the loads on these structures in order to design these structures. Here's an example of some results from one of these finite element models. This is showing the capacity of the foundation system as an interaction curve. So if you're below that curve in a combination of base shear and overturning moment, in theory, the foundation system should be stable, and if you're outside of that curve, in theory, the foundation system should be unstable. On the left-hand side, with low overturning moments, those types of failures are going to be dominated by a lateral pile capacity mechanism, although the piles are battered, so it's not quite as simple as it just being a lateral pile capacity problem. As you continue to the right and you increase the overturning moment, more and more of the axial capacity of the pile is involved. A combined failure is where many of these failures are, so it's some combination of plastic hinges forming due to a lateral mechanism plus plunging or pulling out due to an axial mechanism. And then when you get to the highest overturning moments, you get into almost a pure overturning failure mechanism where piles are pulling out and piles are plunging. Here's an example of a real case. So this is a platform. It's an 8-pile structure that was located in Hurricane Ike in 2008. The red asterisk represents our best guess based on the hindcast data for that location as to what the maximum load was that that platform was subjected to in terms of base shear and overturning moment. And you can see where the black interaction curve is. Of course, the world is not deterministic, so each of those have a probabilistic representation, and what we would like to do is understand how does what happened compare to what we think would have happened, and then to update our ability to predict the performance of these structures based on that information. So here is the basic model. There's multiple modes of failure, so this would be for a single mode of failure. There's multiple platforms and multiple hurricanes. So we're looking at one single mode of failure for one platform and one hurricane in this equation. And we've got what we predict the capacity to be, so that would be using the state of practice, which is the three-dimensional nonlinear finite element modeling and all of the various models that we use for design of the foundations. We have random or aleatory variability in that capacity. So we're trying to account for that. Even though we predict what the capacity is, that doesn't mean we know exactly what the capacity is. And there's potentially model uncertainties. So our models for, say, axial pile capacity are calibrated based on load tests, and none of those load tests have loads anywhere near the kind of loads that we have on these structures in a real hurricane. And so we're extrapolating pretty significantly from those. So there's some model, some epistemic uncertainty in what that capacity actually is. And the same thing on the load side. We're doing the best we can to predict what the loads are based on the mid-ocean characteristics from the hindcasts of the hurricanes. We have 15-minute intervals describing throughout several days of the hurricane passing through the Gulf of Mexico what the sea state characteristics are. But there's variability in those characteristics with each wave and each 15-minute interval, and there's uncertainty in getting the wave heights from the atmospheric conditions they use to develop the hindcast, and then there's uncertainty, even if we know how high the waves are, what the loads are going to be imposed on the structure. So there's random variations accounted for in that aleatory variability, and there's also, again, model or epistemic uncertainty in the models that we're using to predict these loads. Here, we're going to focus on those model uncertainties. So here's an example of one of those model uncertainties. This is on the wave loading component. It's a little bit conservative based on data that we have from structures that were instrumented and put out in the 1970s and the 1980s in the Gulf of Mexico. So we have some sense that there's a little bit of conservatism in our estimate of loads, but we don't have lots of data in real hurricanes. Same thing with capacity. Here's our prior distributions of that model uncertainty and capacity. So the lower left-hand graph, for example, is showing us axial capacity in clay for piles in clay, the kind of model uncertainty that there is in our method, the API method, to predict what the axial capacity would be. The overturning capacity, axial capacity in sand, there's generally the greatest uncertainty of the various models that we have for predicting capacity, axial and lateral capacity. And then the last step is to take what happened and update those prior distributions. So here's what that likelihood function looks like. There's about 20 platforms in different hurricanes with different modes of failure and different performances that were observed that we're incorporating into this big equation that captures how likely is it that these observations would have happened for different sets of values of those model factors. There's 5 different model factors. So for example, here is one of those model factors. That's the bias jacket, or the bias in the jacket strength. So greater than 1 means the bias is positive, or it's the strength of the jacket structure is more than what we would predict using our models. There's 3 different platforms shown there, and on the y-axis is how likely it is that you would have observed what was observed. So for example, the black curve, that's for a platform that survived the hurricane. So if you look at the likelihood function, it's unlikely that the jacket capacity is really small because it survived the hurricane. If the jacket capacity is really big, if it's a big bias, well, then you don't learn very much, because whether it's 2 or it's 1.5, you would still predict that it would have survived the hurricane, so the likelihood becomes flat. The red dashed curve is the complement of that. That's a structure that failed. It specifically failed in the jacket, but not in the foundation system during a hurricane, and it's also showing us how certain values of that bias are more likely than others based on that data. And the blue, we unfortunately don't have many of those, but these are the most informative types of observations. We know it was damaged, but it didn't fail. It didn't survive, it was damaged, it didn't fail, so it's somewhere in between, and so we have a better informative likelihood function for that. And what we're doing is combining all of these together for all of the various modes, and then using Bayes' theorem to update those distributions for the model uncertainties. So here's an example. This is for wave loading. We, based on the data we now have, are more confident. The uncertainty is less in that bias factor for wave loading. It seems to be about what we thought it was, so that's good news. But I want to point out that, remember, there's 5 factors here, and I'm just showing you one of them. So you really need to look at all of them together. Here's the jacket capacity. Again, looking at it all by itself. Again, we're learning more, but it seems to be about what we thought it was. Here's a reminder that this is actually a multi-dimensional updated probability distribution. This is just showing the marginal joint distribution for 2 of the bias factors. But it's reminding us that the kind of data we have isn't overly informative, in that there's a pretty strong correlation between the load and the capacity. In other words, you could increase the capacity and increase the load and get the same observed performance, or you could likewise decrease the capacity and decrease the load and get the same observed performance. So we're capturing that correlation, and at the very end I'll talk about some of the work we're doing to try to uncorrelate these variables with additional information. Here's what we're most interested in as foundation engineers. This is foundation shear capacity. The data we have would indicate that the API method for modeling lateral pile capacity and the way it's being used is a bit conservative. And you can see how that updated curve has moved to the right, indicating that conservatism. Here's axial pile capacity in clay. In this particular case, it wasn't until 2008 that we finally had a failure of a pile in clay. It was a tripod, and we'll talk a bit more about the lack of redundancy in a tripod. But in that particular case, the capacity was almost exactly what we would have predicted it was based on the API method. It was a structure that had been out there for 5 years before it was loaded in the hurricane. So even after 5 years of aging, it still had a capacity that was about what we would predict it would have been using the API method. And that kind of information is reflected in that updated distribution for the bias. It's centered pretty close to 1. And here's foundation axial capacity in sand. We thought we were a bit conservative. We think we're even more conservative based on the data that's coming from these hurricanes, but it's still very uncertain. I want to look at one of these cases in detail just to show you, you can look at it holistically like we have been, but every one of these is really a story into of itself, and the real value, I think, comes from looking at each one of these cases individually and understanding what happened. This is a structure that was loaded in Hurricane Ike. It's an 8-pile structure. The interaction curve would indicate, based on the standards, the state of practice, we would predict that this platform should not have survived that hurricane. It should have failed in the foundation. It did not fail in the foundation. It was still standing at the end of the hurricane. So the structural engineers, when they first went to assess this platform, anytime a platform has seen something that's close to its design loading conditions, you have to go through an assessment process before you can put that platform back into service. And in that, in order to explain this platform having survived the hurricane, they took the geotechnical data from the site investigation and the design. They multiplied the underrange shear strength by 3. So it would have taken like $1 million to drill the boring and do the geotechnical work and produce the report for this, and the structural engineers just multiplied everything by 3. In doing that, they could explain why the platform survived. But if you look carefully at this structure, first of all, they weren't using the lateral PY curves appropriately for an ultimate pushover. They were using PY curves for cyclic loading, which are really for stiffness, not for ultimate capacity. They were using a nominal yield stress for the steel of the legs and the steel pipe piles of 36 KSI, when we know, we've done lots of measurements of coupons, it's closer to 42 PSI or KSI. And so if you account for those two things, you can explain why it survived. And then if you even go further, the structural models have the structure starting at the mud line, and in reality, the legs stick down about 2 meters or 6 feet below the mud line in this structure. And if you account for those leg stubs, you can explain why this structure survived that hurricane without doing anything in multiplying the strength of the soil from the geotechnical site investigation. So the impact of this kind of work, one is it's motivated updating methods to predict lateral and axial pile capacity. These are now being, some of them have already, some are in the process, integrated into the offshore practice. I expect, and I already know because I'm seeing it happen, that these are going to show up in AASHTO and other design guidance that we use for all sorts of foundation applications. Number 2, we've explained why foundations are less likely to fail than superstructures in a hurricane. There was a storyline after Hurricane Andrew that continued on until the early, about 2010, that these platforms were over-conservative in the foundation, that the geotechnical engineers were not doing a good job of design. They were being overly conservative. That's not true. The design methodology, in the way it goes component by component and doesn't look at the whole system, it turns out that that leads to, for structures that have more than 3 legs, and most of these platforms have 4, 6, or 8 legs, it's much less likely it's going to fail in the foundation just because of the design recipe. It motivated a system check, so there is now a system check in addition to component checks in design. This work was used in updating the newest edition of the American Petroleum Institute LRFD design guidelines, which I expect will now inform the ISO counterpart design guidelines, and it improved practice for assessing performance of existing structures, specifically by making sure that there's guidance provided to use realistic values of properties, not nominal values of properties, and trying to explain actual performance, and also making sure that the geotechnical engineers are in the room when the structural engineers are working with the design. And lastly, right now we're working on going beyond what we've already done. There's work in Europe that's hypothesizing that waves are bigger and are creating bigger loads for the same wave height than what our design methods would predict. This is important not just for these offshore structures, but for all of the offshore winds and for all the coastal facilities around the world. If we were to say the waves are bigger and stronger, that's going to have a huge impact. So we're looking back now at this work and we're being more specific. Like this structure here, we can see that it was hit by a wave, but it wasn't a wave that was much higher than those damaged members, and it wasn't much lower than those damaged members. And so we can be more informative in our likelihood function on the waves in order to learn more about both the loading and the capacity of these structures. Thank you very much.
My great honor to introduce the winner of Middlebrooks Award 2021, Professor Richard Bathurst. Richard is Professor Emeritus at the Royal Military College of Canada. In addition to numerous awards, Richard has a distinguished record of service as the president of the Engineering Institute of Canada, president of Canadian Geotechnical Society, and president of the International Geosynthetic Society. Richard, please.
Thank you, Lehman, for those kind words. Thank you to the organizing committee for giving me this opportunity to talk about this paper. That was good news to get the invitation. The bad news, I had to remember what the paper was about. This is the header for the paper, and so you can go to the journal website and download it. If you don't have access, I'd be happy to send you a copy. I'd like to acknowledge my co-authors. First of all, Tony Allen, who some of you may recognize as a former TC chairman of the foundation section of AASHTO, and he's the guy that dragged me into this LRFD business. It's always good to have a guy on the front lines attached to an academic who's looking for some work. Assisting us with this work were Peiwan Lin. He's now a professor at San Yat-sen University in China, and Nazem Bozorgzadeh, who is now working with Farouk Nadim. I don't know whether Farouk is still here at NGI. And I miss both of them very much. The topic, the context of this work is mechanically stabilized earth walls, MSE walls. And these are constructed with relatively extensible polymeric reinforcement materials, in particular geogrids. And quite frankly, it's a mature and proven technology. And here you can see an example of a prop panel type wall, and you can see those layers of reinforcement behind the wall, and the reinforcement is used to stiffen and strengthen the soil and provide stability to those panel sections. Now, the design of MSE walls appears in US and Canadian LRFD codes. And the stiffness method recently replaced an old simplified method in the US AASHTO code. And this is the method which is used to calculate what the maximum tensile loads are in the reinforcement layers under operational conditions. So at about the time that this work was done in the US, you folks were moving from the simplified method to the stiffness method. And the stiffness method is a paradigm shift in our appreciation of the mechanics of the performance of these MSE walls, because it recognizes that it's the stiffness of the reinforcement that controls the loads and not the strength of the reinforcement. So the motivation for this work at the time of writing, so we're going back about 4 years or so, was that load and resistance factors that appear in these codes in Canada and the US for the internal stability design of MSE walls were determined from backfitting to allowable or working stress design, sort of backfitting to classical factor of safety approaches. And hence the objective of US and Canadian LRFD codes to meet a minimum consistent margin of safety in probabilistic terms were not satisfied. That is, we're not satisfied when a limit state function was just satisfied. So the objectives of the work were to carry out rigorous reliability theory-based LRFD calibration for the internal stability of these systems. And from that work to provide resistance factors to be used in the AASHTO code and also in the Canadian Highway Bridge Design Code. And we had our foot in both camps because we wanted to make sure that both of these codes were in sympathy. So if you built a wall right on the border, you would have basically the same animal, okay? The interesting thing about the Canadian code, which distinguishes it from the AASHTO code, is that it includes what we call the concept of level understanding. And this appears in the Canadian Highway Bridge Design Code specifically to reward designers with higher resistance factors for limit states when they have greater information. Now, this slide here identifies the load and resistance terms that appear in internal stability limit states for MSC walls. So you see on the left-hand side, you see the maximum load term, and this is usually it's calculated using an analytical method or model, like the stiffness method. And on the resistance side, we have limit states such as pull out. We don't want the reinforcement to pull out of the backfill, and also we don't want the reinforcement to fail in a rupture mode. Too many buttons? Too many buttons? Okay. So that's the terms, and the limit state function can be formulated in a conventional LRFD format, as you can see on the bottom, and the nominal resistance is multiplied by a resistance factor. We expect that to be a number which is 1 or less, and the load factor is scaled up using a load factor which is 1 or greater. And the objective of LRFD calibration is, what is the magnitude of that resistance factor? So in order to carry out calculations for each limit state, we need a performance function that we can connect to calculations for probability of failure or reliability index. And so here you see the performance function. Rn and Qn are respectively the nominal resistance that you would use in your calculation as a designer, and Qn is the nominal load. And also what you see are model bias values. And these model bias values transform our nominal values to observed or measured or real values if we can measure them in the field. And then of course in the calibration process, we have to multiply the nominal resistance by a resistance factor and the nominal load by a load factor. To carry out these calculations, we have to assume that the bias values and the nominal resistance and load values are random variables, and it makes sense, and I'll give you evidence for that, to assume that they're log normally distributed. So if I presume a value for the load factor, which I pretty well have to do, then I can use Monte Carlo simulation, and I can, for an assumed value, like a target trial value of resistance factor, carry out lots of Monte Carlo realizations and calculate what is the probability that this performance function will be less than 0. And that gives me allows me to quantify probability of failure or reliability index, as you can see in this plot. So the question you might want to ask next is that, well, what is a reasonable target probability of failure or reliability index? And on this plot here, you see a well-known plot for probability of failure versus reliability index. And for these limit states, we use a beta of 2.33, which is a probability of failure of 1 in 100. Sometimes this scares people, But you have to remember that these MSC walls are highly strength redundant. So if one reinforcement layer fails or misbehaves, there are other layers that can compensate. So that's why we use such what may appear to be a low value. So like I said, we can carry out Monte Carlo simulations. However, it turns out that if we assume that these bias values and nominal values are log normally distributed, there is thankfully a closed form solution that we can use to calculate beta if we were doing an RBD analysis. And LRFD calibration is a heavily constrained subset of reliability-based design. And in this formula, which may look a little bit frightening, there are a collection of terms that I have conveniently color-coded. So the green terms are terms that refer to uncertainty in the estimate of the nominal load and resistance terms at time of design. The yellow terms are uncertainty in the accuracy of the load and resistance models, the so-called bias. And then also, there are correlations. There are bias dependencies between the accuracy of the model and the nominal values that you predict using, for example, an analytical equation. So, if I substitute into this equation where I have identified a nominal factor of safety, if I substitute at that location the ratio of the load factor to the resistance factor, I can flip this equation around, rewrite it, and I can isolate the resistance factor and calculate that value for the same statistics if I assume a target beta and a prescribed load factor. And now I have an equation. I don't have to do Monte Carlo. And I can stick this thing in a spreadsheet. And the other advantage of this equation is it exposes the content and the contributions of all these terms. Whereas when you do Monte Carlo simulation, what parameters are affecting the outcome is sometimes obscured. So first of all, how do we calculate or get estimates of these bias statistics? Well, for the load side, we went out over a number of decades and collected from instrumented reinforced soil walls measured loads in the reinforcement. So those are the measured Tmax values that you see here in this equation. And then we simply divided, for the same conditions, the predicted maximum value. And that ratio is called bias. And then we collected the statistics for all of these bias values. We calculated the mean, and we calculated the spread as a COV. And you can see that for the statistics for the load side, the mean bias is about 0.96, which means for this model, it's not a bad model. And the spread is about 36%. And when you plot this data on a CDF plot with a log bias scale, it's fairly linear over most of the distribution, which is visual evidence or support to our basic assumption that these bias values are log normal distributed. And then for the resistance side, we did a similar approach. So for the pull-out limit state, we collected a fair number of pull-out box tests with geogrids and with granular soils, and we did the same calculation. So for every pull-out box measurement, we divided that value by the predicted value using the pull-out capacity model that we wanted to calibrate our limit state with, here is the equation that appears in AASHTO. And again, we did the same thing. We plotted CDF plots. Here you can see that this data really, visually at least, is log normally distributed. But the astute observer will also see that the mean bias is larger than 2, which means that on average, the measured pullout capacity was about twice what we predicted. And there was a fair bit of spread. So now we have the load model statistics on the left and the pullout model statistics on the right. And what we can do is we can put them into this equation. But there are also a couple other terms here that we need to look at. And these are the terms that I've color-coded here in the equation. And these are the correlations between the model bias and the predicted value. Okay? So what it means is that if you look at the load plot on the left, the accuracy of the model is reasonably independent of the magnitude of the load that you calculate. However, on the resistance side, the accuracy of the pullout model is very dependent on what the predicted value is. Now, this is fairly undesirable, but it's a reality. However, we can accommodate this bias dependency analytically within this closed form solution that I introduced earlier. So now let's look at, we've talked about bias statistics. Let's talk about the nominal values. Anytime we do a calculation at design time, the project conditions will have some uncertainty. And we can, using this approach here, include that uncertainty at time of design. This actually can be argued as a method of injecting into probabilistic-based design human experience. And in order to arrange our thoughts in this regard, we went to the Canadian Foundation Engineering Manual. And in that manual, whenever you are doing a design, you can classify that design as falling into one of 3 categories. One category is typical project understanding. Okay, that's the middle text that you see here. So this is where you have typical amount of information, experience, fairly standard technology. But you may also have a situation where you have more information and more experience than typical. And so we call that high understanding or high level of understanding. And of course, you can go the other way and have a situation where, for some reason or another, you have less information than you would typically want. So that's a very important concept, the concept of level of understanding. So in this slide here, you see the 3 qualitative categories, high, typical, and low understanding. And basically, as we move up the chart, we have more confidence in the choice of values that we're going to use in our nominal equations. And so what we had to do, we had to quantify those categories by assigning to them coefficients of variation for the choice of nominal load and nominal resistance. And what we did was we assumed for high understanding, 10%. For typical, 20%. And for low levels of understanding, 30%. And by doing this, we now have all of the quantitative ingredients or quantitative values for our statistical ingredients in this closed form solution. Okay? So we're trying to calibrate this limit state, and we have all of these statistical quantities. We know what the load factor is. It's prescribed. We have a target beta. We can calculate the resistance factor. And as the level of understanding increases, the resistance factor goes up. So this is the point. If you put more effort into improving your understanding of the project, you're rewarded with a higher resistance factor, which means ultimately a cheaper design outcome. Now, there are potential correlations between model accuracy and predicted nominal load, as we mentioned before, and those guys are shown again by in the bottom. You can see those blue guys, but there's also other forms of correlations, and this includes the possibility of a correlation between the nominal load and the nominal resistance. And let me explain that by looking at the nominal load in green beside our wall sketch and the nominal resistance in brown. And if you look at the formulations for those two equations, they have common terms. They both have resistance factor, they both have unit weight. And so if I do Monte Carlo simulation by taking random values of friction angle and unit weight and then calculate the corresponding nominal resistance and nominal load, I can get a scatter plot like the one that you see on the right-hand side. If I then put a linear trend line through that data, the square root of the r squared is the correlation coefficient between the nominal load and the nominal resistance. In this particular example, you can see that there's a significant negative correlation between those two quantities. And the utility of this equation is I can include that in this equation, and it can have a big effect. If you study this equation, you can see it have a big effect on the magnitude of the resulting resistance factor. So now we've got everything we need to do. Now it's just a question of bump and grind. You just go into a spreadsheet, and with those parameters, you can then calculate what the resistance factor is for a target reliability index, a resistance factor on the vertical axis and the reliability index on the horizontal axis. And generally, and as you would expect, as the reliability index increases, the resistance factor goes down, because if you want a higher level of safety, then you need a lower resistance factor. So all of these plots show that trend. But then we can start finessing those outcomes by looking at other things. So for example, let's focus on the right-hand side because the curves are more diverse. So what you see, there's a cluster of plots at the top. And these are for a combination of load and resistance model. And you can see that they have different curves. And each one of those curves is a function of the nominal load and resistance. So in AASHTO, we don't use that, okay? But in Canada, we do. And so if we assign a non-zero value to the COV for the uncertainty and nominal resistance, that will change the altitude and the slope of those curves. The astute audience member will note that some of these resistance factors, if you look up in this plot here, they're greater than 1. Okay? Now, we can't have that. Okay? I think a person's reading a code and had a resistance factor greater than 1 would probably start shaking. But the point is that there's no reason why you can't have a resistance factor greater than 1. It's just convention that we don't. So when we were loading, making recommendations for low resistance factors, if we had a factor greater than 1, we just chop it off, and we know that we would have more safety than this calibration would suggest. If we look at the suite of curves at the bottom, you can see here the arrow is clearly showing that as our level of understanding decreases, then our resistance factor goes down. So the intent of the Canadian Highway Bridge Design Code is satisfied by the outcomes that you see in figures like this. So to use these charts, one would go to the target reliability index value that you want. Say it's 2.33. If you're in the States, you then bounce up to the zero curve here, and out would come the resistance factor of 0.9. So that's the mechanics of using these outcomes. In the paper, they're all presented in tabular form. So in conclusion, what this paper has shown is it's shown that this general approach has the advantage that uncertainty in the accuracy of underlying models that appear in LRFD limit state equations, plus uncertainty in the choice of nominal values at the time of design, are considered explicitly. A convenient closed-form solution is provided that can be used to calculate resistance factors using a spreadsheet. No Monte Carlo. My experience with practicing engineers, as soon as I mention Monte Carlo, their eyes glaze over. But they all know how to use a spreadsheet. The choice of nominal load and resistance factors is linked to the concept of level of understanding. And this has been adopted in Geotechnical Foundation LRFD practice in Canada. And as I mentioned before, it injects human judgment into the calculation of resistance factor and avoids a complaint sometimes that geotechnical engineers have about probabilistic-based design and LRFD calibration is that you remove the human. Okay, well, the human is back. The advantage of the Canadian approach is that the designer is rewarded with higher resistance factors for greater project level of understanding. So if you have more test data, you have more experience. If you have a simple rather than a complex project geometry, we can accommodate that using this concept of level of understanding. So the paper has tables of load and resistance factors for tensile rupture and pull-out limit states. And there's some other papers that we've written that have these tables for other limit states. And these can be used by LRFD code writers in United States and Canada for future revisions of the AASHTO 2020 specifications and the Canadian Highway Bridge design. And in fact, the values that we calculated for the stiffness method are currently in the 2020 LRFD code. What is also of value in that paper is we've done all these calibrations for different load models, different pull-out models, and different combinations. Okay, so you can pick which combination of load and resistance model you want to work with, and those resistance factors are there. And also importantly, we have used the same general approach to calculate resistance factors for other reinforced soil structure problems. So we've done it for steel MSC walls, we've done it for soil nail walls, we've done it for reinforced fills over voids, etc. So it's a perfectly generic approach, but of course you have to have data for calculating what those bias values are. But the MSC industry, due to the efforts of Tony and myself by collecting data over many years, we'd have that data for resistance side and load side. So thank you for your attention.
Next, I'm very pleased to introduce the winner of 2023 James Croes Medal, Professor Armin Studlein. Armin is a professor of geotechnical engineering at Oregon State University. He's vice chair of Geo-Institute Soil Improvement Committee, editor of ASCE's Journal of Geotechnical and Geo-Environmental Engineering, and editor of Journal of the Deep Foundation Institute. Armin, please.
Thank you very much. Well, good afternoon. We're in the home stretch. Thanks for sticking through towards the end, and thanks so much for the invitation to give a talk, particularly among so many outstanding colleagues, and I truly appreciate the opportunity. Naturally, this work couldn't have been done without my collaborators. I should point out that this is an interdisciplinary study, so I've had wonderful cross-pollination with my colleague, Professor Barbosa at Oregon State University, and his doctoral student, Andre Vallejo. But this work really couldn't have been done without the doctoral student who led all the difficult calculations and synthesis. I'd also like to give thanks to access to high-performance computing in order to be able to make this work tractable. But many, many folks have led to this particular honor, so I just want to take a moment to thank those that were involved in the review of this work and the nomination. So thank you for all your service to the profession. Okay. This is a paper and a presentation about differential settlement. So it probably makes sense to spend just a couple moments to identify terms that will be useful. I've got two different diagrams here indicating how structures with mat foundations or load-bearing walls or structures with frame structures with isolated spread footings may deform. In general, differential movements will consist of some uniform movements, potentially some tilt, and differential settlement along the footprint of the structure. And historically, it's been rather difficult to identify rotational movements in such structures. And indeed, for frame structures, we might make some accommodations. So for mat foundations and load-bearing walls, we'll use a relative rotational term, angular distortion, which you may be familiar with, that includes or removes the effect of tilt, but then this becomes complicated for frame structure. So the purposes of this talk will identify relative sag as the angular distortion term. Now, I think we all understand and appreciate the effects of differential settlement on structures. However, estimating what the differential settlement actually may be in terms of its magnitude is a challenge. On the design side for the geotechnical engineer is often the fact that the quantity of loads or their distribution may change throughout the design process, right? And the geotechnical engineer needs to provide recommendations well down in that workflow. But more commonly, perhaps, is the case of an incomplete model of the subsurface, right? And so that introduces the effect of spatial variability, which is the topic of many excellent talks at this presentation that I've enjoyed viewing. Now, because of the challenge of estimating differential settlements, we often design to limit total settlement, knowing that differential settlements are some portion of total. And if we can limit total, then by virtue of that, we should be able to limit differential settlements. And so for various limit states, and we'll consider three throughout this talk, ranging from the allowable limit state, which is a state at which we expect no loss in service to a particular structure, no noticeable cracks in partitions or wall panels. We have historically used something like an angular distortion of 1/500. As we approach different limit states, such as a serviceability limit state, we now may have some interruption to service utility connections to a structure. We may begin to see cracks or other inconvenient but largely cosmetic damage to various structures. Instead, the ultimate limit state is now the most severe limit state that we tend to consider. It's associated with cracking, potentially severe to plastic hinging and reinforced concrete structures, yielding in steel beam structures or columns. Now, there are a variety of guidelines and codes that are available to give sense of what limiting angular distortions are associated with these various limit states. And one thing you may notice is they vary tremendously. Some guidelines make a distinction between the type of structure, and that's great, okay? But these do vary significantly. And in fact, many of these guidelines have drawn from historical observational studies in order to come up with these particular guidelines. And that main historical study is by Skempton and McDonald. So it makes sense just to review some of the authors' thoughts of their own work and database at the time of that study. And there's some useful information in the first quotation there, but main thing is that the data set was largely drawn from traditional structures at that time in 1956. And so in the second statement, you can see that hardly any data and none of critical value so far seem to be available for frame buildings with modern forms of curtain walling and dry construction partitions. These limitations must be borne in mind when reading the present paper. And that was nearly 70 years ago. I believe our connections Our structural details have changed somewhat. Our building stock has been exchanged to a great degree since then. Yet we are still often relying on these angular distortion limit states that virtually stay unchanged, or perhaps not well founded at this day and age. Another motivation for this work is the identification of a critical scale of fluctuation or autocorrelation length, which might maximize the probability of exceeding a particular limit state, including failure. At TC 304, when I served as vice chair along with Chair Zhenye Qing, we had a variety of different studies that are summarized in excellent reports that are available for download at the TC 304 website. I think you have to look through the news items for the releases, but you can download these reports. And both of these reports perform a wonderful survey on this idea of a critical scale of fluctuation. And many of us have been thinking about this concept for about the last 20 years or so. A number of these 25 studies focus on differential settlement, and many make some important discoveries, particularly that by Ahmad and Subra on the effect of anisotropy in the autocorrelation length scale. And one of the main findings from these studies is that the critical scale of fluctuation, that is that autocorrelation length that maximizes the probability of exceeding a limit state, tends to be between 1/2 to 1 times the bay length, or the distance between the footings. And so that's been a pretty consistent outcome of these studies. However, I'd point out that the vast majority were conducted using linear elastic constitutive models for the soils. Some of the other studies have used linear elastic perfectly plastic so that at least some failure state can begin to propagate and perhaps connect through locally weak layers. But they've all largely focused on independent footings such that there's no SSI, that is soil structure interaction, or frame action for a particular structure. Hence the idea to evaluate the system response of structures to differential settlements. So this represents the outline of the discussion. I will present, I'll be a little bit late on the methodology, which is unfortunate. I think it's interesting, but I just want to respect the time that's been granted to me here. So I'll refer you to the paper for some of the dirty details. But after presenting the deterministic responses between assessments that include independent footing responses versus coupled responses, that is, including soil structure interaction and frame action, I'll then walk through some what I think are interesting findings from the probabilistic viewpoint. So briefly on the methodology, we were mostly focusing on construction-induced differential settlements. So we're talking about addition of gravity loads as we add floors, and so the main governing deformation mode is driven by deviatoric strains. This represents the immediate settlement deformation standpoint. We didn't want to run finite element simulations of consolidation because of the amount of simulations we had to do. So we selected a stiff over-consolidated soil in which the loads would not exceed the pre-consolidation state, and that kind of allowed us to proceed under this framework. Our uncoupled analyses allowed us to calculate differential settlement angular distortion readily, quite straightforward, and provided a baseline for comparison to previous studies. When we now move to the coupled analyses, we bring in the soil structure interaction at the footings, including passive restraint at the vertical faces of the footings in addition to bearing resistance. We're accounting for rotational responses, and we can track the redistribution of shear and flexure through the structure in an emergent manner. That is, the response evolves as the demand increases. And then we can make statements about the ultimate limit state of the structural members in addition to that of the, what we have implied as structural ultimate limit states through angular distortion. Again, apologies for the brief introduction of some of our methods, but I did want to point out that the steel structure that we used was driven from a fantastic project conducted in the late 90s following the Northridge earthquake. That's when some moment-resisting connections were discovered to be potentially deficient. And so FEMA and NIST performed a wonderful project evaluating design codes in this manner. And so we selected these standard kind of study buildings as the basis for our analysis. And so this structure has been designed to pre-Northridge 1994 building code provisions for the city of Seattle. And there are a suite of structures that were selected in this manner for that study. So as you can see, the structure's got 4 bays. The spacing is approximately 9 meters between the bays. Bays 1 through 3 use moment resisting beam column connections. Bay 4 as a hinged beam column connection. The structure has been designed using typical strong column, weak beam systems with ductile behavior. We have an appropriate damage model that allows moment rotation responses to go from yield to ultimate to degrade to some kind of residual resisting moment. Our columns are modeled using relatively simple force-based fiber section finite elements acting as the strong column, and our weak beams are modeled using finite length plastic hinge beam column finite elements. Down at the bottom of the structure, we're going to simulate our footing response using nonlinear Winkler foundations. Foundation springs, we use 100 springs per footing at the bottom for bearing response, and we capture nonlinear passive resistance, allowing us to capture rotational effects and tilt. Just for brevity, both of the foundation SSI models will draw from probabilistic undrained shear strength distributions, which are seeded into our random fields that are extended below the foundation in order to account for an additional sense of probabilistic performance. Note that we're using a relatively small factor of safety of 2.5 compared to the relative 3.0. We just wanted to encourage or we wanted to give a little extra push to emergent behavior, and so we thought we'd go ahead and be a little bit aggressive with that, but I don't think our results would change appreciably if we used a slightly larger factor of safety. So I mentioned the strength was simulated or was modeled in a probabilistic manner, and we had to make some decisions for computational efficiency. So given the, I think, currently accepted view that there's strong anisotropy in the autocorrelation length between the horizontal and the vertical direction, we decided, that, and also with review to spatial averaging, that we would treat our random fields in a quasi-2D manner, which would then be placed below the footprint of the structure so that each footing would be impacted by the particular random field that we were simulating. And you can see that we varied the coefficient of inherent variability from 0, non-existent, to 100%, extremely large, and the horizontal scale of fluctuation to something that's extremely small to something that's relatively large compared to the footprint of the structure, which again is about 36 meters wide. Each of these random fields then are seeded with a nominal undrained shear strength that's sampled from a truncated log normal distribution. This is done because we've seen from Shadi Najjar and Bob Gilbert's Norman Medal winning paper that you can have particularly low estimates of reliability if we don't account for meaningful lower bound capacities, and that's driven in part by the undrained shear strengths. So we wanted to take that into account so we weren't being too conservative. And so you can see some examples of the random fields that are applied to the bottoms of our structures, and we're ready to go to make some statements. However, I just want to point out that with 77 combinations of random field model parameters, each simulation having 16 random variables, and with an appropriate confidence level that we're talking about 4 million simulations and about 1 year of runtime on 2 HPCs. So keep that in mind as we go through the results. Now the focus is on probabilistic responses, but we need to understand the deterministic response in order to make some statements about the impacts of spatial variability in the foundation soils. And so I've got a view, and you'll see some of these kind of diagrams later on, but we've got a view of our structure. And note that we've got footing widths that vary across the footprint as shown, again sized identically using a factor of safety of 2.5. And the footing widths are a little bit different because the column loads are different. Column loads are lighter at the exterior of the structure, and there are more tributary sources of load on the interior of the structure, so those increase just a little bit. And so it is that distribution of load that drives the differential settlements and the angular distortions that are distributed below the structure. But in general, we can see that the maxima of differential settlement and angular distortion tend to occur at these outer bays because of that difference in load distribution, which is quite realistic. But in general, even with this factor of safety of 2.5, we're just on average a little bit larger than our typical 1 inch of foundation movement using our nonlinear foundation bearing response model. So now let's compare the uncoupled response, where we're just computing deformations, assuming no soil structure interaction whatsoever, but we still have a nonlinear bearing pressure response. Well, our takeaway here is that there's very little difference in the results. Okay, over here we've got 24 millimeters, here we've got 23. Over here we got 29, there's 29. So there's very little difference, or let's say frame action plays a very small role in driving the differences between these coupled and uncoupled simulations. In fact, the maximum difference is just 15% in terms of differential settlement. But the one thing we can take away is that the coupled response provides a more uniform load and deformation distribution because of that frame action. And that potentially could be important, perhaps in view of spatially variable soils driving larger demands. So let's see if these observations hold. So that brings us to the probabilistic response. And I'll present a variety of figures that have cumulative distribution functions for differential settlement. So here we got differential settlement in millimeters. You'll notice I have 3 different ultimate limit states moving from the left to the right in increasing degree of severity. And this is just one example for Bay 1 of the uncoupled analyses with a horizontal scale fluctuation of 30 meters, or about 3 times the bay width. All right. Our first takeaway here is that the median probabilistic differential settlement is always going to be larger than that of the deterministic. When we have no inherent variability, but we still may have a autocorrelation that's captured, plus the random sampling from our nominal undrained shear strength, we see that the differential settlement is 2.5 times larger for the median case. When we increase the variability, that difference increases by 2. Another thing we can take away when we look across multiple bays, such as the first outer and the first inner bay, and for a couple of different scale fluctuations, is that when the coefficient of inherent variability is low, the likelihood of exceeding any given limit state is relatively insensitive to the spatial variability that you have. But this likelihood of exceeding a particular limit state increases sharply as the coefficient of variation increases markedly above 10%. Now let's put in the responses of our coupled analyses. And you can see that these CDFs all shift strongly to the left. Inclusion of soil structure interaction and frame action results in a strong reduction in the likelihood of exceeding a particular limit state, whether it's the allowable limit state, but particularly for the ultimate limit state, as you'll see. So just a couple examples when the scale fluctuation is relatively low. At the median, we're typically seeing 2/3 to half of the differential settlement compared to the uncoupled analyses, and some of that margin reduces a bit as the scale of fluctuation increases. But in any case, without the inclusion of meaningful SSI and frame action, we potentially will lead to, or at least for steel structures, erroneous conclusions about their reliability in terms of response to differential settlements. Now let's take a look at the probability of an angular distortion exceeding any particular limit state, or P sub E LS. And we're looking at 2 cases of low variability in the foundation soils, and we see that these curves are relatively flat. There's relatively insensitive to the scale of fluctuation. However, the nonlinear and coupled analyses produce notably lower probabilities of exceeding the limit state. As the inherent variability increases and exceeds 10%, we see a rather uniform response regardless of the random field model parameters selected, where the uncoupled or independent scenario has a maximum probability of exceeding the limit state at about half of the bay width. That is, when our autocorrelation length is about half the bay width, regardless of limit state, that appears to be our maximum of exceeding the limit state. And that agrees very well with prior studies, which also included independent systems. When we look at the coupled responses, we can see that the maximum probability of exceeding any given limit state occurs, the maximum probability of exceeding a limit state now begins to vary significantly with limit state severity. This is a result of SSI and frame action to respond favorably to redistribute shear and flexural demands, and thus leading to particularly lower probability of exceedance in terms of angular distortion. One thing you can notice is that when we're at very low scales of fluctuation, spatial averaging of the strength is going to govern the system response. So this is the local minima in probability of exceeding any particular limit state. On the other end, we also have a local minima. It's not as low when we have spatial averaging governing, but it turns out that the physical mechanism driving this effect is that the entire structure is tending to tilt more often and rather have differential movements within the footprint of the structure. So we're seeing mechanisms within the foundations, we're seeing mechanisms within the structure that are prescribing the response in terms of critical scales of fluctuation and maximum exceedance probabilities. So let's just quickly synthesize some of these observations. We see a reduction in the probability of exceeding a limit state that occurs due to SSI and increases with limit state severity or demand. We can simply look at bar charts. If we look at the serviceability limit state and exceedance probability of the serviceability limit state, when we compare to the uncoupled analyses, we can see a modest increase in the reduction in exceedance probabilities, but look at that large average reduction in difference as we get to a more severe limit state or the probabilities of exceeding a more severe limit state. The reduction in probability of exceeding an ultimate limit state is just really large, all right? So the structure is working particularly hard to redistribute the demands. We can take another look at the critical autocorrelation length. It evolves with differential settlement demand. It is not constant. So if we're looking at allowable limit state exceedances, we're generally see about half bay width. When we look at exceeding the serviceability limit state, the critical scale fluctuation, that is when the maximum exceedance probability occurs, that's about 1 bay length. And at the ultimate limit state, we're now looking at the entire structure tending to respond to this uncertainty or the spatial variability in the foundation soils. But just keep in mind those previous graphs, okay, there's a bit of a plateau at these maximum exceedance probabilities. The critical scale of fluctuation is not a precise parameter, okay, but rather the structure responds kind of more smoothly, or at least the exceedance probabilities are approaching this critical case over a larger range of autocorrelations than one specific precise manner. Now, that's all been based on angular distortion. And we think about Skempton and McDonald, right? Damaged states are linked, or limit states are linked to angular distortion. But does angular distortion really map to the structural performance in terms of the ultimate limit state of, let's say, the beams? Okay, this is really what we're after, right? Understanding the probability of poor structural performance. So now let's look at the probability of beam yield, that is the beam rotation exceeding the beam yield rotation. And before we look at the graph shown to the right, let me summarize some of our basic observations from our analyses. Floors 2 and 3 exhibited basically similar responses, even though floor 3 had a lighter wide flange beam section. Floor 4 exhibited the best performance, it had the lightest beam section, but it was furthest removed physically from the demand in terms of foundation movements as a result of spatially variable soils. We see that inner bays are less sensitive to spatial variability than outer bays, and that's because they're able to redistribute to the left and the right rather than just having one adjacent bay to redistribute the demand to. But now if we turn to the probabilities of exceeding the beam yield rotation, and maybe let's look at all of our Monte Carlo simulation results, which are in red. Really, oops, what did I do there? Here we go. The exceedance probabilities are 0 for inherent variabilities that are less than about 20%. Okay, so no chance of yielding these beam sections in terms of all Monte Carlo simulation results. But we can condition our simulations based on exceeding one of these angular distortion-based limit states. And when we do that, we have to have increasing soil variability to see meaningful occurrences of beams yielding structurally. But the probability remains particularly low. On a side note, it turns out that the critical scale of fluctuation for a particular beam rotation to approach and exceed the yield rotation is about 1 to 2 bay lengths. It's relatively local compared to the ultimate limit state for angular distortion. But it's low. How low? Well, we have to change the vertical scale in order to show how low. So this is the structural ultimate limit state probability, and we can compare that to the angular rotation ultimate limit state probability of exceedance. And they're very, very different. They're frequently off by a factor of 10. So we might conclude that the angular distortion limit states set forth in many codes and developed based on observational studies really don't tend to map to our modern or even pre-94 or 94 era steel frame structures. What about other structures? I don't know. We didn't look at other structures. But I expect that unreinforced masonry, which are structures which are much more brittle, may be more well aligned with these current limit state, angular distortion-based limit states. Reinforced concrete structures are probably somewhere in the middle, but we don't know. To conclude, this is one of the last slides of content here. Let's look at the system response. Many of the talks we heard about this afternoon focus on systems, and I think we need to spend more time working with our colleagues in different disciplines to understand system responses. So let's just take a moment to do that. And I've just drawn an example for autocorrelation length that's about half of the bay length with a fairly aggressive amount of variability in the subsurface. And I've got the median angular distortion case in terms of angular distortion from our Monte Carlo simulations. I've got the median plus 1 sigma, or 1 standard deviation, and then median plus 2 sigma, just to see if we can link system responses as a function of where we fall on the distribution of angular distortions computed as part of these simulations. What we see is that for the median case, the largest beam rotations, shown here or shaded here, occur in the bay, not where the angular distortion is greatest, but where we have the greatest gradient or change in differential settlement and hence angular distortion. Okay, but for the median case, we're not even approaching 50% of the yield rotation in our beams. If we look at the 3 cases in sum, it's the median angular distortion plus 1 standard deviation case that produces the largest beam rotations, not median plus 2 standard deviations. In fact, the largest beam rotations occur in the bay in this scenario with the best angular distortion. Okay, here we're looking at maybe 93% beam rotation as a percent of yield, but it's the adjacent bays which are exceeding the ultimate limit state in terms of angular distortion. But if you look carefully, the beam rotations are decaying as a function of distance from this large demand of or gradient in differential settlement. Finally, just to talk about that bottom case there, all of the bays have angular distortions which exceed the ultimate limit state in terms of that criterion, but all of the beam rotations are well below yield, and on the right we see that the maximum is something like 65% of beam yield, even though the footings have kind of largely passed our typical ultimate limit state criteria. So again, it does not appear that angular distortion correlates well to the ultimate limit state of steel members. Okay, so maybe we need to rethink these, the way we identify poor performance, but we also need to look at different systems to see how that system response changes. So thanks so much for your attention. I've just got a couple of concluding remarks which you can see here. I think one of the key findings of our work is that the system will continue to work hard and work harder to redistribute shear and flexure in view or in the face of increasing demand. And so this idea of a critical scale of fluctuation, it evolves along with the severity of the demand imposed upon the structure. And there are differences in the critical scale of fluctuation based on what element or component of the system we're looking at. It's clear that neglecting soil structure interaction and frame action leads to errors in our conclusions. And clearly the benefit of SSI increases with structural demand, and that's good news for us. Okay, I think that's enough. I hope you enjoyed the talk. Again, there's lots of details that I skipped over. I invite you to review the paper. I need to thank my great colleagues and co-authors, that made this work possible, and also for your attention.
Okay, so last but not least, we have the Arthur Casagrande Award that was given in 2023 to Dr. Bryant Robbins. Dr. Robbins is currently Division Chief for the U.S. Corps of Engineers Risk Management Center, where he leads programs and staff related to dams and levees. Before that, he spent 10 years working as a research civil engineer for the U.S. Army Engineer Research and Development Center with focus on risk analysis for erosion-related failure modes for embankments. Dr. Bryant earned his PhD from the Colorado School of Mines. Please join me in welcoming Dr. Bryant to the stage.
Thank you. Thank you for that kind introduction, and thank you to all of you for sticking through till the very last talk of the presentation or the conference. It's been a wonderful conference. If you're anything like me, your brains are full, and I know you're tired of sitting, so this presentation is going to move pretty quickly, be very visual and conceptual, and hopefully a nice way to wrap out the day. Before I get started, I also want to thank the conference organizers for inviting me to give this lecture. I was very surprised because there's usually not a lecture associated with the Casagrande Award, but it was a great privilege to be able to put this together, not just because I get to speak in front of you, but because Arthur Casagrande had a very long history with the Corps of Engineers over many decades, doing some very significant studies for the profession and for the U.S. Army Corps of Engineers. He did so much for our organization that we named our geotechnical laboratory building after him. And that happens to be the building that I started my career at and had an office for 10 years. So I greatly appreciate everything he did for the profession and the U.S. Army Corps of Engineers. And I'm happy to be able to give a talk associated with that award. Before I get started, I'd like to just thank many of the collaborators that had an influence or participated in the research I'm about to present. My advisor, Von Griffiths, the Army Corps for funding the work, and my many colleagues there. Also Del Taris and the many colleagues I've had the opportunity to work with there. And more recently, Joost Pol from TU Delft. So I'm going to talk today about developing a new approach for predicting backwards erosion piping. Backward erosion piping is an internal erosion failure mechanism. There are 4 other types of internal erosion that we treat separately: concentrated leaks, internal instability, often you'll hear the terms suffusion and suffosion used, contact erosion, and stoping or global backward erosion. I don't really like that phrase because it causes confusion with backward erosion piping, so I'll call it stoping. This diagram illustrates the mechanisms. Concentrated leaks occur when water flows continuously through an opening upstream to downstream. That could be a crack, like a desiccation crack as shown on this diagram. More often than not, it's a void along a conduit or through a crack in the foundation. And it's the most dangerous internal erosion mechanism based on historical failures. Backwards erosion piping refers to a process where voids propagate through cohesionless sands in the foundation, as shown on this slide. And that'll be the only thing I'm talking about during this talk today. Internal instability refers to processes where the fine fraction washes out of the coarse fraction. Contact erosion refers to processes where a fine fraction is eroded into an adjacent coarse fraction. And stoping refers to gravity-driven upwards progression of voids. I wanted to highlight that because there's been a lot of confusion in the literature over the last 100 years on what these are. And it's just as important to know what we're not talking about as it is to know what we are talking about. Backward erosion piping was one of the first recognitions of internal erosion processes because it occurred on weirs that were built in India. And I'm going to just walk through the next century because over the next 100 years, there were 1,000 studies conducted, more than 1,000 studies, you can see them by year here, on the topic of internal erosion, seepage, and filters, and yet we're still talking about it today. And so I'm going to highlight some of those reasons why, just briefly to set the stage. In the early 1900s, there was an era of empiricism where creep ratios that I'm sure you've seen in your undergraduate soil mechanics books were used to predict whether or not a dam would be safe against piping. At that time, everything was lumped together and just called piping. And these creep ratios just look at the seepage length versus the safe head that could be applied to the structure. After that, we had an era of filters and seepage analysis. This was kicked off by Terzaghi inventing the filters in 1922 and patenting it. And Casagrande really drove home the concept of using seepage analysis and filters to design dams safely in 1937. At that time, we thought we had this figured out, and we know now that you can safely design any structure with filters, and that's what our default position should be. But there's a lot of structures that do not have filters, and a lot of structures we cannot afford to build with filters economically. During that time period, there were some very significant failures around the globe that prompted backwards erosion piping research in the Netherlands, Germany, and the US, which brings us to the last stage, where you start to see an uptick in research because of those failures in the 80s, and that continues today. Even with all of that, it was not until 2007 that the different mechanisms were clearly defined, and we started to tackle all those problems completely independently. So now I'll just highlight a few observations specifically about backwards erosion piping that we can draw from all of the work that's been done. First, and perhaps most obviously, backwards erosion involves pipe flow and flow through porous media. As a result of this, flow concentrates from the soil to the pipe because the pipe is more conductive, resulting in a nonlinear head profile near the pipe tip. This is very important because if you look at different distances in front of the pipe, you will have different gradients or velocities or whatever flavor of hydraulic loading you want to use to quantify what's happening. And we'll come back to this multiple times throughout this talk. The progression of the pipe is driven by those concentrated seepage forces, and this has long been known. Unfortunately, because the pipes tend to meander in both the field and the lab, it's been nearly impossible to measure what's happening directly at the pipe tips. As a result of this, the methods that are typically used in practice are still based on the average hydraulic gradient across a structure, similar to the creep ratios of Bly and Lane, with the difference being that the more recent developments have many empirical factors that try to account for everything that could relate the average gradient to what's actually driving the progression of the pipe, the hydraulics near the pipe tip. As you can imagine, there's significant uncertainty in these average gradient methods. This chart was produced using Schmertmann's method, and it shows on the y-axis the average gradient across the structure, and on the x-axis the coefficient of uniformity for soils that you might have in the foundation. This is for a seepage length of 500 feet and shows that we would expect broad range, the lines on the chart are probabilities of pipe progression. If we consider a 10-meter high levee and look at a soil with a coefficient of uniformity of 2.5, this chart suggests that we might have a probability of piping progressing to failure anywhere from an average gradient of 0.05 up to 0.25, which for our 10-meter high levee is a difference in seepage lengths of 200 meters to 40 meters, so a significant amount of uncertainty. That's not to say more sophisticated research hasn't been done. There's over 50 studies on numerical modeling. I'm just showing one example here, and some of them are extremely sophisticated, using multi-phase flow models, transient erosion processes, and even coupling with particle methods. Unfortunately, going through all of those studies, not a single study has used a measurable, spatially dependent erosion criterion. And like I mentioned earlier, this is important because if two investigators assess progression based on what's happening at the pipe tip, using two different distances, they're going to get very different answers. Additionally, because there's not a measurable model parameter that can be used, most of those studies are calibrations, and reliable forward predictions are not really possible for every situation generically. So we still frequently see failures due to backwards erosion piping, like this levee failure from the 2011 floods on the Missouri River. This is a costly issue for us. On this slide, you see a picture of Moose Creek Dam, which just went into construction due to backwards erosion piping concerns in Alaska at a cost of $148 million. And we just completed modifications at Herbert Hoover Dike this year after spending more than $1 billion due to backwards erosion piping concerns. So that brings me to the objective of the work I'm going to walk through with you. I set out with my colleagues to develop a reliable predictive framework for backwards erosion piping that's based on measurable model parameters. And to do that, we have to develop a spatial erosion criterion for the reasons we've discussed, come up with a way to measure and predict that model parameter or erosion criterion, develop a model that can use that to make predictions and validate this approach. For the rest of this presentation, I'm going to walk through those steps. So I've already mentioned why we need a spatial erosion criterion. Fortunately, we observed from laboratory tests that a critical head profile exists near the pipe tip. And what I mean by that is, if we have a pipe through a soil sample, we can apply a load and nothing will happen. Even increasing that load, nothing might happen. But at some point, we will reach a critical head profile where any loading above that, erosion will occur, and any loading below that, no erosion will occur. So we should be able to use this to model piping. Unfortunately, the critical head profile directly is not a super convenient form for modeling because it's relative to the head at the pipe tip. So in a model, you would have to track that. For this reason, the concept of a critical secant gradient function was developed to provide a more convenient criterion. Here on the left, you see that same critical head profile with an average gradient drawn from the pipe tip to one point on the profile. This is called the critical secant gradient because it is a secant gradient, a linear average. We can calculate that point at every point along that critical head profile, yielding the critical secant gradient function on the right. 2D conformal mapping solutions were used to develop an analytical expression for that critical secant gradient function, and it actually ended up being a pretty simple expression. The critical secant gradient at any distance x in front of the pipe tip is just equal to a constant divided by the square root of that distance. And that constant can be defined using the head measured at any point on the curve. A laboratory test was developed, as shown on this figure, for measuring the head at points along that curve. The device consists of a cylinder that's 15 centimeters in diameter to contain a soil sample approximately 1 meter in length. The sample is subjected to a differential head until erosion starts to propagate, and the differential head is lowered when the pipe reaches the sensing zone so that the pipe will stop. At that point, we can gradually increase the head again until the pipe starts to progress, and the last stable head profile before erosion occurs is taken as the critical head profile. Here you see a photograph of the pipe progressing under the sensors and sample measurements of the secant gradient, the critical secant gradient, from pairs of transducers. These tests were run on 7 different sands. The first sand was a sand that was procured just locally to test the device in Vicksburg. The other 6 sands actually came from the Netherlands and were used in some of the validation studies that I'll show you momentarily. The range of D50 on the sands goes from 0.15 millimeters to 1.4, and the range of the coefficient of uniformity goes from 1.3 to 3.7. So these sands as a whole cover the range of materials in the field we would typically be concerned about piping. On the right, you see example measurements. We only need 1 point to calculate the critical secant gradient function curve, and so it was calculated using every measurement point. Those are the red lines, and the average of all of those is our best estimate of what the actual function is, which is the black line. As you can see from these results, that 2D conformal mapping equation appears to match the measurements quite well, although there's a lot of questions remaining still about whether or not the cylindrical shape of the sample and that 2D equation apply in more general 3D situations in practice. And we'll take a look at that in the validation. For that best estimate curve, we get the C value, the constant that goes into the critical secant gradient function. And from the results of all of those tests, we were able to develop a predictive equation for the C value that's a function of the median grain size, the D50, the coefficient of uniformity, and the soil void ratio. So now let's talk briefly about a model. I'm not going to go into all of the details, but in general, the model that was used was quite simple. It was a steady state model. You just see the steady state groundwater flow equations. And the Darcy-Weisbach equation was used to model the steady state flow in the pipe. So we have two coupled domains. A steady state model was chosen because I'd like to start simple since we don't have something we believe in yet, and also because most of the experiments are conducted in a piecewise steady state way, so it's easy to validate that these ideas work using a steady state model. The pipe was represented in the model using an equivalent hydraulic conductivity. That's what the K sub P is that's shown on the slide, and that just relates the pipe dimensions to the flow that we would expect through a 1D pipe with those dimensions modeled using the Darcy equation. So we're modeling the pipe as soil, but just making sure that the flow through the pipe domain in the model matches what Darcy-Weisbach equation would have yielded. This is really convenient because we can use any steady state groundwater model. It's the exact same solution. We're just changing what we're integrating into the conductivity matrix over the pipe domain. You can formulate that equivalent pipe permeability for different types of elements, just matching the geometry of the elements to the geometry of the pipe and making sure the flow quantities come out the same. And algorithms were developed for pipe widening and pipe deepening so that the dimensions of the pipes are automatically determined, as well as automated pipe progression. I'm not going to talk about the widening or deepening. You can see my PhD thesis or papers for more information on that. But I will talk about the automated progression because that illustrates how the critical secant gradient is used in a model. For a minute, imagine we're looking at an element immediately upstream of the pipe. From your numerical model, the average gradient over that element is our best estimate of the secant gradient in the model over some distance x in front of the pipe. We can calculate the critical value of the secant gradient corresponding to that distance, and if the secant gradient in the model for under given boundary conditions exceeds the critical value, the pipe will progress by switching that element from the soil domain to the pipe domain. Because it was a steady state model, there are not that many additional parameters beyond a normal seepage analysis that are needed to do these predictions. We need the critical secant gradient function, the grain size, which is used for the algorithms that assess the pipe widening and deepening, and the water viscosity to calculate the equivalent permeabilities. So now let's take a look at some validation. The first case is a small-scale experiment that was conducted in the Netherlands. The upstream boundary is a constant head boundary on the right. Oops, sorry. The downstream boundary is a hole exit condition that's also constant head, and everything else is closed. This particular sand was one of the ones that we tested in the cylinder, so we have measured values of the critical secant gradient and measured values of the soil hydraulic conductivity. This particular model was an excellent validation case because the pipe happened to pass under the sensors. This is showing the critical pipe geometry and position. And so we can use this to validate the hydraulics of the model and see if our assumptions are adequately representing what's going on in the pipe. And we can also use this to validate the idea of using the cylindrical lab test to measure the critical gradient function, because this particular experiment was more of a three-dimensional case. This just shows the relatively simple finite element model that was built of that experiment. The pipe was set to the position that was observed in the lab. And the downstream and upstream boundaries were set to the heads that were measured in the laboratory. Like I mentioned, we don't need the critical secant gradient function, but we did need the grain size because that is how the depth of the pipe was calculated. And here you see the resulting modeled head distribution across that sample as compared to the measured values. There were a few points in the pipe that were higher, but looking at the photograph, the pipe missed those sensors, which is why they're elevated. Otherwise, in general, it appears that the assumptions for the pipe hydraulic calculations are quite valid. Additionally, based on this head profile, the C value in the critical secant gradient function was calculated for this experiment. The value from the three-dimensional box experiment was only 8% lower than the cylinder. And this was good news because I would expect that if the cylinder is biasing the determination of that function, the cylinder would have a lower value because it has less three-dimensional flow and convergence. And so the fact that the box was lower than the cylinder gives me some confidence that we might be able to measure it in the more convenient cylindrical shape to get values to use. The second case is a similar experiment, but it has a layer of coarse sand in it. And this is a good validation case because it provides more complex erosion patterns, and we can see if the piecewise steady state algorithms are capable of replicating those. On this screen, you see the simulation of the erosion pattern on the left and the applied upstream head in the chart on the right, as well as the head profile down the entire top of the model on the bottom right. So let me play that again. A couple things to note: the erosion pattern spreads out completely along that coarse sand interface before penetrating into the coarse sand in one spot, stopping, and then failing the barrier in another spot, or the coarse sand layer in another spot. That is actually what was observed in the experiment, and more impressively, the predicted head of 1.28 meters was extremely close to the experimental value of 1.3 meters. And again, this was using the measured critical secant gradient function and the measured hydraulic conductivity from the cylinder in this simulation. The last validation cases I want to present are larger scale. These are over a meter in length. They were conducted by Rebecca Allen at the University of New South Wales. And these are good cases for validation because they have different exit conditions. So one of the tests had a hole or a slot, one of them had a plane, and one of them had a slope. That gives us different hydraulic patterns to see if this modeling approach is still working in a general sense. For the model inputs, the hydraulic conductivities for the sands were reported in her thesis, so those were used directly, but I did not have any indication of what the critical secant gradient function was for those sands, so the predictive correlation I showed you earlier was used to estimate what the critical secant gradient function was. Here you see the results in terms of the differential head on the sample. The numerical values are on the left, on the y-axis, and the experimentally measured ones on the x-axis. Again, we get very close agreement suggesting that there's some validity to this idea of using the critical secant gradient function as your erosion criterion and the steady state modeling approach. So a few conclusions we can draw from this work. The critical secant gradient function provides a measurable, spatially dependent erosion criterion and appears to be able to be used to reliably predict piping. Additionally, we can predict the critical secant gradient function from basic soil properties. So if we can't measure it, we have a way to estimate that in practice. And then lastly, the preliminary validation studies are showing quite promising results. I'm not convinced yet that it works, though. So next steps that need to be taken are we need to pursue field scale validation of this approach. Additional measurements of the critical secant gradient function need to be made. And ideally, we'll have enough information to do back analysis of various case histories to convince ourselves that this is useful in practice given all the uncertainties that we encounter in the field. Thank you for your attention.
I would like to take the opportunity to congratulate the award winners again and thank them for presenting this work to us in this conference. So we'll open the floor to questions. We have some time left. Questions to our presenters? Yes, Lisa.
I have a question for Bryant. Actually, thanks for the beautiful presentation. And actually, we experienced this back erosion a lot in levees along the river, Zhujiang River in China. But our difficulty is that we didn't exactly know the soil properties inside of the levees because it is constructed over a long history. So is there any measures for you to use your method to deal with this kind of problem? Thank you.
Yeah, I think it's just like doing the seepage analysis, right? For levee systems, they're so long, we often don't have properties for where we're doing our designs. And you can still use these tools estimating what the soils in the foundation are. The most important part in my mind is without a physics-based model, we don't have a model that we can propagate those uncertainties through. And so having this available will allow us to do sensitivity analysis or probabilistic analysis based on what we believe is there, where we can't easily do that now for all generic situations. So I think, yes, we can use it for that, but it's just like any other tool.
Any other questions to any of the speakers? Yes. Thank you, Christina.
I have a question for Professor Bob Gilbert.
Sure.
In your talk, you talked about the system check for offshore platform, and you use the failure records, survival records, and damage records to update your performance. So I'm wondering if you differentiate any failure type, damage type, or failure modes in your study. Thank you.
Yes, so the observed performance had to do with details about whether it was damaged and where it was damaged and how it was damaged in terms of failures of members and failures of connections. So yes, there's all of that structural detail in what's going on. And the system check that's been added, really the issue was tripods were not anywhere near the same reliability as the other structures, and so there's now a system check where you use something like a 500-year return period loading event, and you just make sure the factor of safety or the pushover capacity at least can withstand that of the system itself. Thank you.
Thank you, Bob. Any additional questions? Yes, please go ahead. Christina.
Thank you. My question is for the last presenter. In your gradient model, depends on granulometric characteristics, no? Coefficient of uniformity D50. What is the representative volume in which those characteristics need to be evaluated for as an input to your model?
Yeah, that's a great question. And I don't know how small scale you can go before the continuum model breaks down. But obviously, the approach I took is assuming that that entire function, the critical secant gradient function, is in a homogeneous material. And so you can't go out, you can't apply it at a scale where that assumption is no longer true.
Thank you.
Any other questions? Yes, Sina.
Take a question to Brian. Have you ever measured?
Do you want to come?
Yeah, you have done extremely interesting test on piping. Have you ever measured local hydraulic gradient near or around a pipe?
Yeah, at scales of 2 centimeters up to 100 centimeters away from it. Yep.
How big a difference between local and nominal gradient?
Oh, I see what you're asking. Extremely different. So local values are significantly higher than the average values.
Thank you.
We still have time for one question. Last opportunity. Yes. You're going to take that opportunity.
Is for Professor Bathurst now?
Sure.
At
There you
first
go, Richard.
he thought he was going to escape, but no, I was curious because, as you mentioned, this correlation between magnitude of load and bias in the model, I think. Do you have any idea of why this is happening?
Yes, the pullout example is a classic example. And the reason is that when people developed that pullout capacity, they wanted to have a conservative model. They wanted to have a model that underpredicts the measured results. Because then when you put it into your design, you will be automatically safe. So that's the reason. And in the old days, that's what people used to do. On the load side, they developed models that over-predicted the load, because that way you're going to be safer. And on the resistance side, you want to have a model that under-predicted resistance. But it screws up calibrations of the type that we're using, because what we really want is we want a model that's accurate. And then you can apply to that model your own level of safety, not some level of safety that some guy used when he was plotting all the data and wanted to have a lower bound on his model curve. If that helps.
Okay, so with that, and before we close, I would like to take the opportunity again to thank everybody who made this conference a success. In particular importance, I want to thank the technical committee chair, Jenny, who is still here, for all the effort that he did for the technical program. That was an amazing effort. Thank you, Jenny. On the technical committee also, we have Zinan, Lei, Sarah, and Jason, who were also phenomenal in supporting us in achieving this. Finally, we have the organizing committee consisting of the following esteemed individuals: Vaughn, Adrian, Lizanne, Jinsong. Some of them could not attend from different places. Kimberly, Martin, Timo, Iason, who is here, and Andy. Again, the final thanks go to the GI staff and leadership, Brad, Lucy, Sean, and Christina. I might be forgetting other names, but these are the ones I interacted with the most. So with that, I would bring this conference to a close. Thank you very much for attending, and thank you for the speakers for today's session. Thank you. The final thing, Brad's directions, of course, before we leave. Every attendee, again, I want to remind them that they can get their full conference proceedings from the registration desk. PDH forms are available there. Also very important, if you've parked in the DoubleTree garage, don't forget to let the desk know when you are checking out. And thanks again to all the general sponsors for helping support this event. Thank you. Congratulations for your
Good job. Good job.
I couldn't have done it without you guys.
You can see what.
Yes, of course I can. I'm taking this off and taking that off. Life is, if you want to say life in general, it's good. We have like 1.5 million tourists that came from July, starting July. No places and restaurants from now until the month, no places in hotels. And at the same time, the country has just